Hello everyone, welcome to chapter 7. So in this chapter we'll discuss quantum theory and atomic structure. So in this lecture we'll talk about the nature of light, atomic spectra, the wave particle duality of matter and energy, and finally end with the quantum mechanical model of the atom. So let's start with the wave nature of light. So visible light is a form of electromagnetic radiation. So the wave properties of electromagnetic radiation are generally described by three variables. The first one is frequency, second is wavelength, and third is amplitude. Frequency is the number of cycles per second. Wavelength represents the distance between a wave that travels, distance of a wave that travels in one cycle. And amplitude is the height of a wave or a crest or the height of a wave crest or the depth of a trough. So the speed of light here is a constant, and that value is given by c, which is v times lambda, which generally is 3 times 10 to the power 8 meter per second. So what is the relationship between frequency and wavelength? So frequency is inversely proportional to wavelength. So when the wavelength is small and the wavelength is large, the frequency is small. When the wavelength is moderate, the frequency is a little higher, and the shorter the wavelength, the higher the frequency. So frequency and wavelength have a reciprocal relationship. Now, in terms of the amplitude, what does amplitude generally represent? Amplitude represents the height of the wave. The height of the wave is similar to the brightness. The higher the amplitude, the brighter the light. The lower the amplitude, the dimmer the light. Now, so what is the electromagnetic spectrum? So you start at gamma rays, which have really high frequencies, and you end up with radio waves, which have really low frequencies but high wavelength. So visible light can be divided into VIBGR, so violet, indigo, blue, green, yellow, orange, and red. So, and each of them range from around 400 to 750 nanometers. So let's try a problem here where we are interconverting wavelength into frequency. So you have a dental hygienist that uses X-rays with a lambda of 1 angstrom to take series of dental radiographs while the patient listens to a radio station of lambda 325 centimeters and looks out of the window with a bright blue sky of 473 nanometers. So what is the frequency of the electromagnetic radiation from each of the sources? So they have given us the velocity, which is 3 times 10 to the power 8 meter per second. So we know that C here is the product of lambda times f. So using this formula, we can find every one of these frequencies. So let's start with the first one, X-rays, with a lambda of 1 angstrom. So angstrom is a unit that represents 10 to the power negative 10 meter. Now, so we know that f here becomes c by lambda. C is 3 times 10 to the power 8 by lambda is 1 times 10 to the power negative 10. So it becomes 3 times 10 to the power 8 times 10 to the power 10. So it becomes 3 times 10 to the power 18 hertz. So this is the frequency of the 1 angstrom light. Notice that wavelength here is really small. That's why the frequency is really high. Next, let's look at the 325 centimeters. So the 325 centimeters here so let's try and use the 325 centimeters. So the second one we have 325 centimeters. Convert it into meters, so which becomes 3.25 meters. Sorry. We have 3.25 meters. So the f becomes c by lambda. So 3 times 10 to the power 8 by 3.25. So when you calculate 3 over 3.28, 3 over 3.25, the value is 0.923 times 10 to the power 8 So when you take 110 out, you get 9.23 into 10 to the power of 7 hertz. So this is the frequency. This is the frequency of the light that is given here. So this is how you can find the frequency. So using this principle now, next we have lambda equal to 473 nanometers. So let's try and solve the problem next one. You have lambda equals 473 nanometers. So 473 nanometers becomes 473 times 10 to the power negative 9 meters. So 1 nanometer is 10 to the power negative 9 meter. So F becomes C over lambda. C again is 3 times 10 to the power 8 by 473 times 10 to the power negative 9. So 3 by 473 times 10 to the power 8. 10 to the power negative 9, when it goes up, it becomes 10 to the power of 9. Now let's try and find 3 divided by 473. So the value becomes 0.0063 times 10 to the power 17. So when you move 3 zeros here, so this one here, you have to move 3 places. So 0.0063. So when you add 10 to the power 3 here, you get 6.3 into 10 to the power. So remove three values from the power. So it becomes 14 hertz. So this is the frequency. So this is how you can calculate the frequency of all the values using the simple formula F equal to C by lambda. Now let's look at different behaviors of waves and particles and how to differentiate the behavior. A wave in general behaves the same way as a particle. So when you take a wave generally bends, so creating an angle of refraction. But a particle changes its position gradually rather than changing it suddenly like a wave. A wave would change it suddenly, but a particle changes it slowly. Now the same thing when you look at it in terms of waves that are bending around a small opening. When you look at a wave, it creates wave fronts. But when you look at a stream of particles, so think of this like a time glass. You have a sand glass where sand pours down. When you take sand pouring down, you notice that the particles go in a straight line rather than dispersing throughout the system. So this is the difference in behavior between a wave and a particle. Now the initial idea for light was first conducted by the diffraction patterns that were created by the Young's double slit experiment. When you pass a single source of light, a coherent source of light, through 2 slits, it creates a stream of bright and dark fringes. So this bright and dark fringes happen due to constructive and destructive interference. So what happens now? At one point, all the peaks will match. So when the peaks match, it creates a bright fringe. When the peaks collapse, what will happen when they are in the opposite directions? They collapse each other. That creates dark regions. So this series of bright and dark regions, these are called fringes. So this is how the light behaves as a wave. This is the first discussion of how light behaves as a wave. Now let's discuss energy and frequency. So a solid object in general emits visible light when you heat it up to 1000 Kelvin. So this type of radiation is called as black body radiation. Now the color of the light changes as the temperature changes, because color here is related to the wavelength and frequency, while the temperature is related to energy. Combining both comes the equation E equal to NH nu. We also call this the Planck. So we also call this the Planck's law of radiation, or Planck's law of black body radiation, where N is a positive integer, H is the Planck's constant, and E is the amount of energy. So this is the experiment that we commonly know. When you heat up something, it produces color. The hotter it is, the more redder it is. So this is a common theme that we can see here. So this brings us to the quantum theory of energy. So the quantum theory of energy says that any object can either emit or absorb energy, certain amounts of energy. And this energy comes in terms of packets. We call that quanta. So it undergoes quantization. So quantization, it occurs in fixed quantities rather than being continuous. And each fixed quantity of energy, we call that a quantum. Now, an atom changes its energy by emitting or absorbing one or more quanta of energy. So we call this delta E. Delta E generally is given as the change in energy is given as delta N times h nu, where N can be a whole number only. So N here is the one that represents the number of particles. H nu is the energy of each individual particle. So h nu is the energy of one particle. Del nu is the number of particles that change. So this was first shown by the photoelectric effect, so which was first proposed by Einstein. So what did Einstein do? He striped a metallic screen with powerful radiation. He noticed that the powerful radiation actually emitted electrons. Notice that until then people had the idea that light was a wave, and Newton, using his photoelectric experiment, he proved that even as a wave it can have energy, and that individual energy particles are called photons. So this was the first term, the name comes through. So let's take an example. You have a student uses a microwave oven to heat a meal. The wavelength of the radiation is 1.20 centimeters. What is the energy of one photon of this microwave radiation? So the formula is E equal to NH nu. So the value for H is 6.63 into 10 to the power negative 31. Sorry, 6.626. into 10 to the power negative 31 joule second. So this is the value of Planck's constant. Remember the value for Planck's constant. Now, so with this into consideration, now we have one photon, so which is n equal to 1, and we have to know the velocity. So how do you find the velocity? So they have given that this is a microwave oven, so which means that it is still microwave radiation. Microwave radiation also travels at the speed of light. So nu here is not velocity, but nu here is actually the frequency. So remember that nu here represents the frequency. It's not V actually, it's a curved V. So V here represents the frequency, but they have given us the wavelength. Wavelength is given as 1.20 centimeters. Convert it into meters, you get 0.012 meters. Now, with this into consideration, what can we write here? We know that nu here is C by lambda. C here is 3 times 10 to the power 8 by 0.012. So 3 divided by 0.012 becomes 250 times 10 to the power 8. So we can write it as 2.50 into 10 to the power of 10 hertz. So substitute the values into the formula. So E is 1 times H is 6.626 into 10 power negative 34. Sorry, this is 34 times 2.50 into 10 to the power of 10. So using the values now, you have 6.626 into 2.50, so it becomes 16.565 times 10 to the power negative 34 times 10 to the power negative 10 gives you 10 to the power negative 24. So when you can write this, you can write 1.656 times 10 to the power of negative 23 joule. So this is the value of energy of that particular particle, one photon of the microwave radiation. This is the amount of energy that each photon carries. Now next let's talk about atomic spectra. So when you pass hydrogen and heat it up to a certain temperature, we know that every body, when you heat it up, it releases radiation. So the radiation that is emitted by hydrogen is generally classified under the spectra. Under the visible spectrum, you can see that you have 4 different wavelengths that are generated: 410 nanometers, 434, 486 and 656. So why does this happen, and how can you explain this radiation? This radiation and the wavelength can be explained by the Rydberg equation, which can be written as 1 by lambda equals R times 1 by n1 square minus 1 by n2 square, where n1 is the first energy level, ground state, and n2 is the higher energy levels. R here is as the Rydberg constant, which is 1.096776 into 10 to the power of 7 per meter. So this was first explained by the Bohrs model. So Bohr's atomic model, so Niels Bohr first postulated the idea behind why the atomic spectra exists. So he postulated that the hydrogen atom has only certain energy levels, and he called it the stationary states. And each state is associated with a fixed circular orbit and the electron around the nucleus. And the higher the energy level, the farther the orbit is from the nucleus. Now, when the hydrogen electron is in the first orbit, the atom is in its lowest energy state. The atom that is in the lowest energy state is called as the ground state. Now, the atom will not stay the same way, so does not radiate energy while one of its stationary states. What will happen is that when it changes one state to the other state, it either does it by absorbing or emitting a photon. Now, the energy of the photon equals the difference between the energies of the two energy states. So, when it jumps, when it goes from a lower energy to a higher energy, it absorbs energy. When it comes back from a higher energy to a lower energy, it releases energy. Now, when the electron is in any orbit higher than or equal to 1, we call that an excited state. So, remember this term, excited and ground states. So, what happens here in terms of the absorption spectrum and emission spectrum? When the electron jumps from the first orbit to the second orbit, and it absorbs some energy. From the second orbit to the third orbit, it also absorbs some energy. From third orbit to the fifth orbit, it also absorbs some energy. The same thing happens in reverse as well. In reverse, it undergoes emission, where from fifth state to fourth, it can release energy. Fourth to third releases energy. Third to ground state also releases energy. So this energy release is what we consider as the atomic spectrum. So remember that we are initially heating up the hydrogen gas. When you heat up hydrogen gas, what you're doing is basically giving it energy. Now once you remove that heating up, it starts losing energy. That losing is converted into emission spectrum. Now if the energy level directly falls from the highest energy state to the ground state, the radiation that is really emitted is ultraviolet radiation. So when you go directly into the ground state, you release ultraviolet radiation. When directly you go into the second energy state, that releases visible radiation. When you directly come to the third energy state, it releases infrared radiation. So this here was given what we call series of names. So these series as Palmer series, Leiber series, so Lyman series, these are some of the common names given. Now the idea was that when the textbook here, think of textbook falling from a higher state to a ground state, which means that there is an energy difference. That energy difference can be calculated as delta E equals E final minus E initial, which is given by the formula negative 2.18 times 10 to the power negative 18 joule times 1 by N final square minus 1 by N initial square. So let's try this problem and see if we can use those formulas and write down the problem here. So hydrogen atom absorbs a photon of UV light and its electron enters the N equal to 4 energy level. Now remember that when it absorbs UV light, you're starting from the ground state. So remember that depending on the type of radiation, you will know where you are starting. So here you are going from N equal to 1 to N equal to 4. Now first thing they're asking you is the change in the energy of the atom. So delta E can be written as minus 2.18 into 10 to the power negative 18 joule times 1 by N final square minus 1 by N initial square. So this is N initial, this is N final. So we can have minus 2.18 into 10 to the power negative 18 joule times 1 by N final is 4 square minus 1 by 1 square. So when you calculate the value, so you should get a value of 2.04 times 10 to the power negative 18 joule. So this is the amount of energy. Now, how do you find the wavelength here? So we know that the formula for E is, so delta E is delta N times h nu. So we are finding the lambda value. So we can replace nu with C by lambda. So delta E becomes delta N times h into C by lambda. So lambda becomes, so delta N times hc by delta E. Now here we are talking about one single photon. So delta n becomes negligible. So we can simply write the formula as delta lambda equals hc by delta E. So h is 6.6226 into 10 to the power negative 34. C is 3 times 10 to the power 8 divided by delta E is 2.04 into 10 to the power negative 80. So which when you calculate, you end up with the final answer 9.74 into 10 to the power negative 8 meters. When you convert it into nanometers, it becomes 97.4 nanometers. So that is how you know that the emission is a UV radiation. So the most common way to measure an object is by using a spectrometer. So a spectrometer is the way by which we determine different objects' atomic spectra. Now let's talk about the next topic, the wave-particle duality of matter. So matter in its original state has two alternate forms. So matter and energy are alternate forms of the same entity. So they are the same entity, but they have different forms. So the forms here refer to the wave-particle duality, the first equation that was given here. So all matter exhibits properties of both particle and waves. So the first experiment that proved this was electron diffraction experiment. Even electrons have wave-like motion, and therefore they have only certain allowable frequencies and energies. That was first given by the de Broglie hypothesis, which basically stated that every particle has both a mass and so it both behaves as a particle and a wave. So that he mentioned that the wavelength of that particular particle can be written as lambda equals to h by mu, where m is the mass and u is the speed of the particle. So what are the wave restrictions that it can have? For example, it's allowed to have a n equal to 3, it's allowed to have a n equal to 5, but it's not allowed to have n equal to 3 1 by 3. So wave motion here is in restricted systems. So a slow electron would have a lambda value of 7 times 10 to the power negative 4, but Earth, because of its big mass and less velocity and high mass, results in a lambda value of 10 to the power negative 63 meters, which is very, very, very low. So this is the idea behind de Broglie wavelength. So use the principle here. So you have everything given. So use the formula lambda equals to h by mu and try to calculate the de Broglie wavelength. So pause the video right here and try to solve this problem. So one of the primary uses of using this was the first time is to use false color electron micrograph of blood cells. So electron microscopy was first discovered by using this principle of the idea that you can reflect electrons as waves. You can use electrons as waves because they behave as waves. They can also, end up becoming a good substitute for light rays. And because of the wavelength that electrons have, because of the wavelength range that the electrons can operate until, fast electrons can operate until, we can use these to look at really detailed images of objects. So this is an example of electron microscopy used to create this kind of ideas here. Now, what are the major observations and theories leading from classical theory of light to the quantum theory? Was the first observation was black body radiation by Max Planck, where he said that the energy is quantized and only a certain values are allowed and you should only get it in multiples. The second was the photoelectric effect observed by Albert Einstein, where he said that light has also particulate behavior and behaves as photons. And you have atomic line spectra proposed by Niels Bohr, and where he said that the energy of the atoms is quantized and the photon emits when electron changes orbits. Now, since energy is wave-like, perhaps matter is also wave-like. So the observation was that the electron beam is diffracted by a metal crystal proposed by de Broglie. So de Broglie basically stated that all matter travels in waves and energy of the atom is quantized due to the wave motion of electrons. Now, since matter has mass, perhaps energy also has mass, which was proposed by Einstein and de Broglie, where he used the famous Einstein mass energy equivalence, E equal to mc square. So where he said that a body of a certain mass will also have a certain amount of energy. So this gave rise to the quantum theory, and where energy and matter are particulate, massive, and also wave-like. So because of this problem here, this brings up a big problem of uncertainty, is that when you're able to follow through and understand the uncertainty here, what is the uncertainty here? Uncertainty is the amount of error that you get when you're trying to calculate one value and the other value cannot be calculated easily. Now, a body traveling, so Heisenberg's uncertainty principle was the solution to explain this uncertainty. It states that it is not possible to know both the position and momentum of a particle moving at the same time. So there is only one chance: either you can calculate the position or you can calculate the velocity, but you cannot calculate both of them at the same time with high accuracy. So what is basically saying is that if you want to increase the accuracy of position, then you can decrease the accuracy of the velocity. If you increase the accuracy of the velocity, it decreases the accuracy of position. So this was perfectly stated with the Heisenberg uncertainty equation, which is delta x times m times delta u is greater than or equal to h by 4 pi, where h is the Planck's constant and m is the mass of the particle. So the more accurately we know the speed, the less accurately we know the position, and opposite, and vice versa. So what is given here? An electron is moving near an atomic nucleus that has a speed of 6 times 10 to the power 8 meter per second, plus or minus 1%. What is the uncertainty in its position? So how do you find the value here? So they have given you delta u, which is 1% of 6 times 10 to the power 6. So calculate 1%, which is 0.01 times 6 times 10 to the power 6. So which becomes 6 times 10 to the power of 4. So they have given you delta u, and they are asking you to find the uncertainty in the position. So we know the formula is delta x times delta u times m is greater than or equal to h by 4 pi. So delta x is the value that we want, so h greater than or equal to h by delta u times m times 4 pi. So substitute all the values and you end up getting the answer. So that value becomes, so when you substitute everything into the formula, you end up getting an uncertainty of 1 times 10 to the power negative 9 meter. So next let's talk about the quantum mechanical model of the atom. So which was first proposed by Schrödinger. So Schrödinger basically stated that rather than the electron being at one single place, he said that electron, rather than being at a single place, is generally found in a given region, and he said that it's not a deterministic value but a probabilistic value, which basically says that what is the probability or the chance of finding the electron at a particular position. He explained that by using Schrödinger's wave equation, which allows us to solve the energy states associated with a particular atomic orbital. So he basically stated that the square of the wave function gives the probability density, and which is the measure of the probability of finding an electron of a particular energy in the particular region of the atom. So for an s orbital, this probability, electron probability, is very high at a single region. So as you go farther and farther away, the chance of finding the electron becomes lesser and lesser. So this is the s orbital's shape. So this is how we propose the s orbital shape. So the easier way to explain this is by using the quantum numbers and orbitals, atomic orbitals. So a simple atomic orbital is generally specified by 3 quantum numbers. The first one is the principal quantum number, which is a positive integer. So the value of the principal quantum number indicates the relative size of the orbital and therefore its distance from the nucleus. Second is the angular momentum quantum number given by L, which is an integer from 0 to n minus 1, so which is basically dependent on the principal quantum number. And the value of L depends on the shape of the orbital. And the third one is the magnetic quantum number, or M. It is an integer from minus L to plus L, so it depends on the angular momentum quantum number. And the value of ML basically indicates the orientation of the orbital. So for a principal quantum number of 1, the angular momentum is 0 to n minus 1, so 0. and magnetic momentum quantum number is negative L to plus L, so it becomes 0. Now for the second principal quantum number, you end up getting two different angular momentum quantum numbers, and for each angular momentum quantum number you get a momentum magnetic quantum number, so which is 0 here, and for one you get negative L to L, so minus 1, 0 and 1. In the same way, when you have 3 here, so let me write it down in a separate part. So let's say if you have 3 here is n equal to 3, then L becomes 0 to n minus 1. So it can have 0, 1, 2. So n minus 1 is 2, so it can be 3 different values. So from 3, we get 3 different angular momentum quantum numbers, 0, 1 and 2. And m value stays from negative L to L. So 0 is negative 0 to 0 is 0. And for 1, you get 3 different values. So negative 1, 0 and 1. For 2, you get 5 different values, negative 2, negative 1, 0, 1 and 2. So this here represents the n value, this 3 represent the L value, and these values represent the m values, ml values. So this is how you can find the magnetic momentum quantum numbers. So let's say we have what values of angular momentum and magnetic quantum numbers are allowed for a principal quantum number of n equal to 3, and how many orbits are allowed for n equal to 3. Orbitals are allowed for n equal to 3. So let's start with n equal to 3. So 3. So L is 0 to n minus 1. So 0 to 3 minus 1, which becomes 0 to 3, 2, which is basically 0, 1 and 2. So for a principal quantum number of 3, you can have 3 different orbitals. So L here represents the number of orbitals. And next for the magnetic momentum, so each m here is from negative L to L. So notice that there are 3 different ones, so which means that you start from 0. For 1 you get negative 1 to 1, so which is negative 1, 0, 1. And for 2 you get negative 2, negative 1, 0, 1 and 2. So this is how we can find the numbers. So use the same principle now. So remember this part, when depending on the L value, we can also say the orbital. If L value is 0, then the orbital is the s orbital. If L value is 1, it is the p orbital. If L is 2, it is the d orbital. And if L is 3, it's the f orbital. So L here represents the orbital. So simply, whenever we want to write the particular position, we can write it there. So n here represents the stalk, n here represents the orbit, and L here represents the orbital. So when you want to write the position exactly, so it basically represents that n, L, ash. So n and L, we can write it directly. So for example, for the first one, n is 3, L is 2. So for L2, then the orbital is d, so we can write 3d. So because it's 3d, so we can say that the orbital is in 3d. And because they are asking us to give the name and magnetic quantum numbers and the number of orbitals for each sublevel, now let's try and find for 3d here. When L equal to 2, we know that m is from minus L to L, so which is from minus 2 to 2, so which becomes minus 2, minus 1, 0, 1, 2. So this is the value for m. So this is how we can write. So use the same principle now and write down the rest of the values. So pause the video right here and try to solve the rest of the problems. Next, let's talk about identifying incorrect quantum numbers. So here they have given us n and L and m values. They are asking us to find whether there is a possibility of if there is anything wrong here. Let's take the first one. So when n is 1, so name is 1. L is 1, so which is p orbital, so 1p, fine. Now we know that m here. So notice the problem here is that when n is 1, L is 0 to n minus 1. So which means 0 to 1 minus 1, so it should be 0. So which means this is the part that is wrong. So it shouldn't be 1, it should be 0. So like this, try to find whether the values are correct or not. So try to predict which one of the values that is given here is wrong. Pause the video right here and try to solve this problem. So these are some of the shapes of the s orbitals. S orbitals are rounded. The higher the orbit number, the quantum number, the higher the size. So 2p orbitals generally have a dumbbell shape, and because there are 3 different orbitals, so for each p, so an s orbital only has one of them. P contains 3 sublevels. Remember that p is, so p becomes from L equal to 1. So all the possible values are -1, 0 and 1. So there are 3 different suborbital levels. For 3D here, the D has a flowery shape. The flowery shape comes because of the fact that when you take a d orbital, so for d, L is 2, so the possibilities are -2, -1, 0, 1 and 2. So there are 5 different possibilities of the values. So these are the 5 different ones. So this is the combined 5d orbitals. And this is the shape of an f orbital. So f orbital contains, so it becomes 3 here. So -3, -2, -1, 0, 1, 2, 3. Notice that each suborbital contains 2 electrons, and you have 7 different suborbitals. So from this we can write down that an s orbital contains a maximum of 2 electrons. A p orbital can contain a maximum of 6 electrons. D orbital can contain a maximum of 10 electrons, and f orbital can contain a maximum of 14 electrons. So remember this principle here and the number of electrons that it can hold. So with this, we end our lecture on quantum theory and atomic structure.